Well, hello YouTube. I'm back for the fifth part in my four-part series on the curvature of the Earth. I'm realizing I'm about as good as Douglas Adams when it comes to naming things the same way as he named The Hitchhiker's Guide to the Galaxy trilogy. Uh, anyway, that just came to mind if there's any fellow Douglas Adam nerds out there watching this video. Anyway, when I first did my drop height video, I had this picture in mind that the flat earthers bring out a lot for drop height. How much, when you go away from the ball, how much does it drop for each mile on the surface? Okay, so this is what I was thinking of when I was doing my how do you get this answer video. So it was pointed out to me that the original 8 inches per mile squared calculation was actually not that. He said you have the slightly wrong, Dark Star told me, I have the slightly wrong geometry for the 8 inches times mile squared calculation. The drop is actually angled towards the center of the Earth, not perpendicular to the tangent line. Okay. And he promised, so I went and had a look, and of course he was absolutely right. And that even crossed my mind when I started the video, because when I said to you we were going to shine a laser level out, set it on the surface of the Earth and shine it out over the water and see how high it was above this person's head, or see how far up on the boat it was going to go. Starts here, now it hits up here. Obviously, if we're trying to see how high this is above a person's head, we want that person to be standing upright. And on a globe, vertical changes. Vertical is towards the center of the globe. So obviously, it's this height we're looking for, not this one. So we'll just get rid of that, and we'll go about calculating that little bit of height on the surface of the Earth, or off the surface of the Earth. I'm going to do this a little bit differently. We're going to look at this, first of all, I'm going to use radians instead of degrees. And if you haven't been exposed to radians, I'll just give you a quick recap, or a quick idea of what they are. Where degrees divides a circle into 360 parts, radians actually divides a circle into 2 pi parts, which is just a little bit more than 3. There's more than 6. 1 pi is a little bit more than 3. So half the circle would actually be pi radians. So if we let this be theta, and I want to compare theta to the entire circle, now instead of writing theta over 360, I'm going to write theta over 2 pi. Now the rest of the circle that I have here, of course this is a radius, and so is this one. This is the distance we're trying to find. I'm going to let that be h. This is the distance between the 2 points on the Earth's surface. I'm going to let that be capital D. And we know that this is perpendicular here because this is a line tangent to the Earth at this point, and this is the radius coming to the point of tangency. And we talked about that in a previous video. So remember that this angle in the middle, theta, when compared to the entire circle, will be in the same ratio as the arc length from between those 2 points, which we're going to let be d, compared to the entire circle, which is 2 pi r, which is the formula for the circumference of the circle. Now, if I want to get theta by itself, I'm going to multiply both sides by 2 pi. Now looking over here, we have 2 pi times theta and then divided by 2 pi. Well, if I multiply theta by 2 pi and then divide by 2 pi, I'm right back where I started from, so that's just theta. And same thing over here, I'm going to multiply d by 2 pi, and then the first thing I do is divide by 2 pi, so why would I bother doing it? Because I'm right back where I started from. So what that actually means is theta is equal to d over r. Remember, d is the distance between the 2 target points that we're talking about, and r is the radius of the Earth. The next thing we're going to do is find h. And I'm going to do this a little bit more with algebra instead of worrying about having all those nasty decimal numbers. Now, since this is a right angle triangle, we can still use trigonometry. And if we're going from this angle in here, this is the adjacent side, and this over here is the hypotenuse. So cos is what we're using again. So we're going to find the cos of theta, and I'm going to leave that as theta right now. Later on, we're going to put in the d over r. But cos theta equals adjacent over hypotenuse. So the adjacent is r, and the hypotenuse is r plus that little h, that little extra height. So now let's go about solving for h. First thing I'm going to do is kind of the same thing I did over here. I'm going to get rid of this denominator by multiplying both sides by r plus h. And when I multiply it over here, it's going to go away because if I multiply and then divide, I'm right back to where I started from. Now over here, I'm going to use the distributive law and multiply cos through the brackets to get an expression that doesn't have brackets. So on this side, we're going to have r cos theta plus h cos theta. And on this side, of course, we're left with just r. Now our goal, remember, this is what we're trying to get by itself. So I'm going to subtract this on both sides. H cos theta equals r minus r cos theta. And I can make one little simplification here. Since they both have r, instead of what I did up here when I multiplied cos through, now I'm going to divide the r out. I'm going to take the r and put it in front of a set of brackets and divide it out of each of these two things, which are going to be left in the brackets. So r divided by r is 1, and r cos theta divided by r is just cos theta, because that means times. So r cos theta, r times cos theta, divided by r, the two r's are going to cancel each other out. And this side is still just h cos theta. And to get h by itself, we have r times 1 minus cos theta divided by, I've got to get rid of that cos theta, so we're going to divide by cos theta. Now the last thing that I'm going to do before I actually plug some numbers into my calculator is substitute in what we know theta to be. Theta is d over r. So r times 1 minus cos d over r divided by the cos of d over r. Put brackets around that. Now for this particular example, since the last time we calculated drop height, we let d be 1, I'm going to do the same thing here. So we're going to let d equal 1 mile, which means that our two targets are 1 mile above the surface of the Earth. Not above the surface of the Earth, along the surface of the Earth. And of course, r is the radius of the Earth, so we're going to use 3959 miles. So let's plug those into our formula for finding h, since h is what we want to find. H equals 3959, bracket 1 minus the cos of 1 over 3959, there's lots of r's in this expression, divided by the cos of 1 over 3959. Let's pull up the calculator and see what we get. I'm thinking it's going to be very close to 8 inches. So this calculator, remember, this I can type it in exactly as it looks. A lot of calculators won't do that, so you got to be careful. 3959 bracket 1 minus cos bracket 1 divided by 3959. Whoops, that didn't. 3959, there we go. End bracket. Notice that it put the little degree up there. Remember I told you that we weren't working in degrees, we're working in radians? I have to make sure my calculator knows that. So I got to click this little thing that says degree, and now it tells me that we're working in radians. So I'm going to close off that bracket, and now we're going to divide by the cos of 1 divided by 3959, end bracket. Now, what are we going to get here? 0.00012 miles. Okay, so that's in miles because we were working in miles. We need to change that because that doesn't mean a whole lot to us. Remember, we're looking for inches. So let's change it into feet and then into inches. So in order to change it into feet, we need to multiply by 5280. That's how many feet there are in a mile. So let's pull that calculator back up and go times 5280. And there's our answer in feet. And since it's still smaller than a foot, that's feet. Since it's still smaller than a foot, we're going to change that answer into inches by multiplying by 12. 8.002. So let's take a minute here now that we've got what this is the correct geometry for the 8 inches per mile squared formula. We're going to see how that compares to what we got before. So I've made some modifications into my spreadsheet where we had the drop height before in miles, feet, and inches. And we're going to put that to 1 to see that we get the 8. So we're going to take a look. I'm going to put a box around that one too. Excuse me. And this up here is our 8 inches per mile squared estimate. Okay. And we're going to see how far we can go before this number, our estimate, varies from these two things. Now, the first thing you want to know is these two things are not exactly the same. Obviously, they're not the same because we are looking at two different lines here. And a lot of times flat earthers tell me that that angling away is going to make all the difference if something can be seen over the horizon, or because something doesn't look like it's angled away, or because something doesn't look like it's shorter than it was before, that means that the earth is flat. Well, that angle really, for the stuff that we can see along the surface of the earth, this angle really means very little. And I'm going to show you, because the difference between what this was and what we now got here, which is all because of that angle, right? The difference between those two lines was, gosh, they're the same all the way down to the last 2 digits on here, 3 digits on here. Okay, that is, let's go through them here. Tenths, hundreds, thousands, 10,000s, 100,000s, millionths. So they're the same down to the millionths of an inch when you're talking about 1 mile along the surface. Now this is going to change a little bit. Obviously the estimate is the same to hundreds. Okay, so these three things are virtually indistinguishable from each other. Let's try something a little bit more. How about 60? Since 60 is that infamous picture of the Chicago buildings across there, what would it do in 60 miles? So now we can have a look that in 60 miles, the difference between that vertical building and, or sorry, not the vertical building, that vertical line, and the other one is approximately 3 inches. Okay, so that angle really isn't doing all that much when we're talking about short distances on the Earth. So these two things are very, very close together. But they're getting farther away from this one. So this estimate, even at 60, is starting to get, well, it's still not bad. It's only about 6 inches. What about at 100? At 100, we're starting to, these two things are starting to deviate a little bit more. That angle is meaning something a little bit more, but still, it's only, you know, it's not very much. We're talking about 26 inches. Okay. Something like that. And when you're looking at something that is really tall, a few inches is not going to matter too much. Now, this isn't a direct comparison to how tall the thing would look. I'm just showing you that at those distances, if really that angle is not making that much of a difference. But notice again that they're really starting to deviate from this estimate. And we'll do one more. I'm going to go 600. And now you can see here that these two have really parted ways, and they've both parted ways a lot here. We're talking about the difference at 600, where this is no longer a good estimate. This was 2.88 million. So we're looking at tens of thousands of difference in inches. Okay. So I think I'm going to leave that there. We've fixed this to be the better drop height. I've also shown you a little bit more with algebra. I hope you understood it as I walked you through with algebra rather than using the decimal numbers. I find using numbers a whole lot more cumbersome than actually just putting in the letters for their place until we're done. Okay, so we're going to leave that there. Thanks for watching.